Okay, so as I mentioned in another video, going to start a whole new um, section of questions, about 15, I think. I'm not quite sure exactly how many, but the following topics will be covered in the new material, and we'll spend a full week just on the new material, and then we'll go back and try to pick up any problems, any gaps from the previous lesson sets. And everybody has some. There's a few there. So got to make sure that going forward, foundationally, everything that's on that sheet, we'd like to have you understand. So we're going to be covering rational functions during the second half of the semester and their associated limits. The unit circle, going to try to get good at the unit circle so that if I ask what's the tangent of 29 pi over 3, boom, give me a quick answer. And to get ready for that, I'm encouraging folks to look at Intro to the Unit Circle and What is a Radian. Those videos will support that endeavor. Learning how to work with trig graphs and equations. We'll get some introductory work there. We're also going to be talking about putting cubics in graphing form, which is based on completing the cube, which is just one step up from completing the square. We'll also, once we learn how to put cubics in graphing form, which is just one step more, just one step more than putting quadratics in graphing form. Then after we learn that, there's one step more, which is a 5-second step, very similar to the problem that we've been looking at here. Let's say this is 8,3 with an a value of 2, ax squared value, right? So it's cup shape up. What are the roots? A lot of you now simply write 8 plus or minus the square root of 3/2 imaginary. Some of you are still trying to sort out why it's imaginary, and we can keep talking about it until you do sort it out. It's important to sort out. Once we put cubics in graphing form, once we know the rate of change at the point of inflection, it's as quick and easy as that to find that x and that x for local max, local min. All right, so that's coming our way. Rome wasn't built in a day, so it's going to take a little bit of preliminary effort to get up and running, take us a couple of days, but you shouldn't be as afraid of that process now as you were at the start of the class when I overloaded you with material. The only way that we're going to have this be, the only way I think you're going to remember this is if you overlearn it. Okay, I hope you've done enough equations of a line in the last 2 months that 50 years from now, you can write it just as quickly and easily. Okay, I don't think I will be, but hopefully you will be. All right, let's see. Did I miss anything? Exposure. Oh yeah, geometric relationships. We're going to look at the cubic and the squares and the cubes in greater detail so that we can give you some exposure to derivatives and integrals. So that when you get to that study, and most people are getting there now, whether the foundation is there to really support that endeavor or not, the purpose of this course is to give you that foundation, and I think we're moving in the right direction. And I'm going to start looking at rational functions with you briefly in just a moment. But you know, it's midterm. It's one of those moments to take stock, to take inventory. Where are we? Where are we trying to go? And we're trying to learn how to learn. And to me, you got to work with numbers. So I've asked you to memorize some things like the square root of 3 over 2, the square root of 3, square root of 2 over 2. Have you done it yet? As a group, no. But I believe in internal motivation, so I'll just continue to say, I hope you get there, because if you can understand math, you got to work with numbers. And if you don't have a feeling for the size of a number, pretty hard to get a feeling for the discipline. So let's have at it right now. I got Rene Descartes' cousin. This is that's another Rene. Yeah. Okay. Anyway, was able to move the cart that I'm using today to our first rational function. So I've got 2 lines. I'll call this one line 1 and line 2. And let's divide line 1 by line 2, and let's try to stay away from numbers for a moment. Even though I just said you got to have a feeling for numbers. So let's get started. Let's start right here. I chose those words very carefully. Let's start here. What does that mean? Let's start here. I'll pause the video for a second and give that a little thought. Well, I think we've got a calculation here. And those calculations have answers to them. Depending upon what you start with. Let's start here. Well, I hope that comes to mind as some X value. I mean, that's what we work with. X, Arabic for the word something. We have to start with something. So how would we describe this something? Well, we got Rene Descartes to help us with that. It's called the x-axis. And all it is a ruler. And what do you put on rulers? Numbers. And what do you put? You got to start somewhere. And generally speaking, we start with 0 in our mind's eye. And then we start to talk about other numbers and the easy ones, the user-friendly ones are integers, and we count and we move to the right. So what can I say? We're starting here. Well, without any numbers, I mean, this could be 0.01 or it could be a billion. But I can tell you one thing. If this is our origin, then it's a positive number. And if I'm pushing to the right, then those positive numbers keep getting bigger and bigger and bigger. So let's take one a little closer to home here, closer to 0. Let's actually start with that one. I'm changing up on the fly. And then we'll talk about that one. Well, if I put a number into the calculation, it comes out as a different number. And I can't use X to describe the different number. I know I've seen on tests where folks think that that's 4 and that's 4 also on some graphs. I don't think so. I think it's a different number. So what's that different number? Well, in math, we usually use the letter Y. I guess because it comes after X in the alphabet. I don't know why Y was decided upon. That's above my pay grade. And so how do we show Y? Well, Rene Descartes gave us another ruler, the Y ruler. And the vertical distance from here to there is the value I get on line 1 when I get started with that X value. And the value I get on line 2 will make little circles, little dots. That's what I get. And I'm asking you to divide. And so if we're dividing, we have this amount and we have this amount, which is, looks like it's a little bigger amount. I don't know what that is. I can guess. Let's see. That's 1 unit, say. So 1, 2, 3. I think I'm getting a third. I think when I divide these things, I get a third. A 1-to-3 ratio. So why don't we give some numbers to this now? And let's say that that's what I get. We'll call that 1/3. Well, what happens when I go back to the original? Let's start there now. All right. Let's put in the boom, 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 boom. I don't think that's changed any. I think that's exactly what we put in the numerator, but the circles, the little dots, whoa, they're a lot bigger. So how many times does that fit into that now? I don't, again, unless I have some real numbers in front of me, I can't accurately state, but it does seem like this will fit into that less times. In fact, it doesn't fit into it at all. It just fractionally fits in. And so I'm going to erase and say, okay, let's call it 1/4. Well, what happens is I move down the x-axis, more dots. That stays the same. And it sure seems like I know where I'm headed. And that, when I said the associated limits, let's call this function f of x, the calculation f of x. What's the limit as x goes to, where am I headed? I keep considering bigger and bigger x's. I think I'm headed to infinity. And what are my fractions going towards? Well, it seems like 1/3, 1/4, probably a 5th, probably a 6th. 1/3, Oh, let's get on the number line, find out. Let's put 0 here. Let's put 1 there. There's 1/3, there's 1/4, there's 1/5, there's one. And I didn't really spend much time getting an accurate scale there, but I hope you can see, and I'll use an arrow for starters. It's going to 0. Okay, that's good. Now what happens? All right, so let's get rid of that and just realize it's going to 0. Well, what happens is I move closer and closer to this moment. Well, that distance is getting what? That distance, the dots are getting, whoa, there seems a reversal where actually the line 1 vertical is bigger than line 2. Ah, well, that fits in more than once. And what happens as I get closer and closer to this X value, that squiggly line, smaller and smaller. Oh, no, the squiggly line's the same, excuse me. It's the dots. I should have been saying the dots. Fewer and fewer dots. Fewer and fewer dots. That still stays the same. That, you know, that seems like a constant. Konstant. My grandson says I should put a C there, but no, it's a constant. So we're going to say K. I keep telling him cats, K-A-T, and I don't know what he's learning. He's not getting much of an education at his school. I'll keep talking to him. All right, so I think it goes more and more times. In fact, that distance right now might fit into this 5 or 6 times. So right about here, looks like I'm 5 or 6 right there, 5 or 6 times. And I think I can make the dots, or my squiggly line's going to be the same, but dots, you know, they might even get a half of a dot. And a half of a dot, maybe even a third of a dot, maybe a fourth of a dot, maybe a fifth. And every time this thing goes from a third to a fourth to a fifth, it fits more and more times. I think it's going up to positive infinity. The smaller I make that. Now, the smaller I make that. So what do I say over here? I say the limit as X goes to the circle. I circled an X value. I better put the X value in the circle. But I didn't do it from both sides. No, I went from bigger numbers to smaller, and mathematicians like to put a little plus sign there to indicate that. And so where am I headed? Positive infinity is what we said. Yeah, something really strange happens once I get past this. Wow. My dots are now below the x-axis. I think they're negative. And yet the squiggly line is still representing the value of the constant. And now I got a very small negative number into a constant. Well, I think the limit as X goes to that dot, but now I'm considering that X value from the left of this function. I got a feeling it's going to negative infinity. I think I got the same thing there, except now at this X value, I think things are heading to negative infinity. And it sure looks like when I'm at this X value, I got squiggly line up. It's always the case. And I've got squiggly line or dots down. You know, in this particular picture, they almost look exactly the same magnitude. I think I'm heading to -1. I think that's, oh, that might be the y-intercept. Yeah, that might be the y-intercept. And then as I start looking at these X values, which I'm not going to positive infinity anymore. I think I'm going to those X values, negative infinity. And I think I'm going back to 0. All right. I think I'm going back to 0 over here. I've got line, right? I keep forgetting whether I'm doing dots or scratch. I've got the same amount for that constant. That y value hasn't changed, didn't change over here, right? But what's different? Oh, my negatives. My negatives are getting bigger and bigger and bigger. All right, so let's give some some names to these unrepresented. Well, they're represented by altitudes, but let's get a function that replicates this. All right, what you might have been looking at if you had it coming to you in terms of numbers. Well, maybe we have a 5. Maybe that altitude, that constant was a 5, and maybe we were looking at x minus 1. And so that x is 1. And let's look at all the things that we could have said. None of that's going to change. But if I was graphing this, what's given? What can I see right from the get-go? Right from the get-go, I can see -5 in this instant is our y-intercept. 0 gets me -5. I can see 1 is undefined. X equals 1 is undefined. If that's 1, then -5 is much lower than that. So let me put this on the other side and start again. So let's say 0 gets me -5. That's -5. Then that might be x equals 1. And what I'm suggesting is you can't divide by 0, 1 minus 1. So I'm going to get asymptotic behavior. We said on this side, we headed towards 0. I know that because x to the 0 is the number 1. This is x to the 1. And when that exponent is smaller than this one, tends to go towards 0 as a fraction. And we know that this went to -infinity, and it's still going to go to 0. So we have to label our asymptotes. Let's label this. So I did. Okay, out of habit. Good, I did. And I don't think I have any x-intercepts. No x-intercepts. I don't think. You can try to plug some numbers in and see if you get a 0. Be my guest. No x-intercepts. And I think you can kind of see that from the get-go because there's no way to make the numerator 0. If you see this number change to 0 in the next 30 seconds, definitely give me a call, write an email, something. We'll get you some help. Got some nice people up the hill that will talk to you. Okay. You haven't seen it change, have you? And I don't think you're going to be able to get 0 out of that fraction. I want you to know all these things. I want you to know how to do that in 10 seconds or less for a problem of this difficulty. It's not going to happen overnight, but we got to start the conversation. We just started. All right. And while I'm at it, I might as well give you a cubic. What the heck, just to show you that it's, we'll do it a month from now with derivatives, but right now we'll do it without. Typical problem that you've been seeing, 2x cubed minus 6x squared plus 10x minus 5. That looks familiar to me as a test question this past week. So the way I'm going to do this is a little different than a month from now. A month from now, I'm going to do it in a quicker fashion, but let's take minus b over 3a. That's going to get us the x value of the point of inflection. 6 divided by 6 is 1. I picked a nice easy number. I'll put 1 in. 2, this should be -6 without looking. There's my 3-to-1 ratio, and opposite, quadratic, it's 2-to-1. We'll talk about the geometry of it as we go along during the second half of the term. Plus 10 minus 5 gives me a point of inflection of 12 minus 11, 1. It goes through 1, 1. Imagine that. All right, so let's get a little y-axis going. I know if I put a 0 in, I'm at -5. 0 gets me -5. And 1, 1 is the point of inflection. Yeah, seems like that's already dominating. So I may not get maxes and mins out of this. Let's make this -10. So I'm going to start again. All right, doesn't change anything except here. So I definitely want to highlight a rate of change that's negative. All right, so 2 -6, -16, -21, plus 2, -19. So now 1 gets us -19. I like that better because I know the y-intercept is 0, -5. And now the end behavior, I know I'm going up, I know I'm coming down, and I know I'm going back up again. And here is the coordinate 1, -19. And we've done this much in class. I have talked about the rate of change here. Oh, it's going down. I should have looked at that first. That's why I said I would do it quicker and easier in a month from now. I know I'm going down to 10-to-1. I should have done that first. 10-to-1, 0, -5. So therefore, I now have something that looks more like that. Good. And point of inflection is where I change from concave up to concave down. We'll call that one -19. All right. So I think we're good now. And so how do I know the rate of change? This is the one thing that I haven't really stressed with you. I've mentioned it a few times. Little formula here, C minus 3AH squared. Of course, I erased y equals 2x cubed minus 6x squared minus 10x minus 5. There. That was the original. So what's C? Minus 10 minus 3, A is 2. What's H? H is minus B over 3A, so 1 squared. That's minus 16. So I'm going down at 16 to 1 at this instant. That's the minimum rate of change. That's the fastest I'm declining right there. All right. And so therefore, I said you could get the roots, not the roots, the value of the max and min here in 5 seconds or less. So let me do that for you. I've got an x value here of 1 minus. Over here, I have an x value of 1 plus. Oh, minus 16. I have maxes and mins. So therefore, I have 1 minus the square root of 16 over 3 times A. A is 2. That's over 6. That's that x value. You might guess now that this one is positive, 16 over 6, and you'd be right. So that's not rocket science. So what is this in graphing form? X minus 1 cubed minus 16, x minus 1 minus 19. Now, if I didn't make any careless errors, we've got ourselves a graph. We can see the maxes and the mins. We can see we have 3 real roots by the look at, well, I can't say that yet until I find this y value. So I'd have to find that y value. And at that point, you're probably working more with calculators anyway. Yeah, but it would be nice to understand the origins of where these graphs come from and why. And that's going to come from looking at completing the cube, the geometry behind it. So there's some work to be done. And we got 2 months. We don't have to knock it all out of the park day one. All right, that's just the start of the conversation. And 5 days, 5 lesson sets from now, I'm hoping that, we're a lot further along. All right, so that gets us started. Tomorrow I'll do that first lesson set. It's about 15, 16, 17 problems, I'm guessing. And just a little preview of what's coming. And stay safe, stay warm. And I always have my buddy overseas to check and see if I did anything stupid, which I usually do. Getting old. All right, ciao.